We are ready to start now. I want to start by saying welcome everyone to our Advances in Dementia webinar, res- uh, Dementia Research webinar series that is hosted by the Alzheimer's Society and the Toronto Dementia Research Alliance. A little bit of housekeeping as we get started. This session is being recorded, so I will ask that you refrain from providing any private information in the chat. The recording will be made available on both the Alzheimer's Society of Toronto YouTube channel, as well as the TDRA website. If you have questions as the presentation is occurring, I do encourage you to type them into the chat and we will get to as many as we can um, after the presentation has been finished. So this webinar series discusses recent updates in dementia research and highlights research studies that are occurring all across Toronto. Today, our speaker will be speaking about measuring visual abilities and electrical signals in the brain for early detection of Alzheimer's disease. A little bit about the Alzheimer's Society for those who are perhaps new. We are a registered charity and our goals is to provide free counseling, education, programming, and information to people who are living with dementia, their care partners, whether it's family and friends, healthcare professionals, as well as the general public. A few things to note is that you do not need a diagnosis to access any of our services, and you also do not require a referral. So if you have questions, you are more than welcome to contact us in one of the formats below. We do run a number of activities, both educational as well as social for for primarily people living with dementia. If you are curious about everything that we offer, please do check out our calendar of events and programs that is listed below. Now I'd like to tell you a little bit about our partner, the TDRA. The TDRA was established in 2012 and is a collaboration among the University of Toronto, Baycrest, the Centre for Addiction and Mental Health, Ontario Shore Centre for Mental Health Sciences, Sunnybrook, Unity Health Toronto, and the University Health Network. Together with its partners, TDRA aims to strengthen the link between basic science and clinical research to better understand, prevent, and treat dementia. And now I would like to hand it to my partner, Natalie Dren, to tell you a little bit more.
Thanks, Julie. Can we just move to the next slide? Great. So my name is Natalie. I manage knowledge translation and communications for the Toronto Dementia Research Alliance. And we've partnered with AST on an initiative that makes research more accessible to everyone. So the Toronto Dementia Network, or TDN, is a website that lists dementia-related programs and services across Toronto. On the website, we created a section called Research Studies, which lists dementia studies that are open for participation across the city. And each study listed is led by TDRA affiliated scientists and has been approved by a research ethics board. So there are studies for people living with Alzheimer's disease and other types of dementia, mild cognitive impairment, those at risk of developing dementia, and healthy volunteers and caregivers. The studies are all summarized in plain language, and to get started, the website link is shown on the slide in orange, and information about the TDN can also be found on the AST and TDRA websites if you're interested in learning more. We can go to the next slide. Okay, so on the website, there are two main pathways. First, you can browse for a study using search terms, filters, and quick searches. When you find a study you're interested in, you can fill out the contact form to be connected with the research team who will enroll you in the study if it's something that you're eligible for. Or at the bottom here, if you're not sure where to start, you can fill out a questionnaire to be matched to a study. And any information that you enter in the form or any on the website will be securely stored and protected. Okay, next slide. Okay, and this is what the website looks like. So when you're on the page, if you're looking for something specific, so for example, Alzheimer's disease studies, you can type it into the search bar along the top. You can then hit submit with that term, or you can apply more filters like the type of study you're looking for, an age group, target population, or the study location, and then hit submit. Alternatively, you can use the quick search buttons we have in the blue boxes. If you'd rather fill out a questionnaire to be matched to a study, you can click the Match Me to a Study quick search box, or if you scroll all the way to the bottom of the page, you'll see this orange button that says Can't find a study you're interested in, and that will also take you to the questionnaire, so you can access it that way. Each study summary describes what the study is about, who can participate, the location, and the time requirement. Again, that's all in plain language. And the study being listed or being discussed today is actually listed on the TDN, so you'll be able to read more about it and connect to the study teams there. Great, we can move to the next slide. And now I'd like to introduce our speaker. And before I do so, just a reminder to keep any questions till the end of the webinar for our question and answer period, but feel free to type them in the chat. As Julie said, throughout the webinar, we'll keep track and we'll be sure to answer as many as we can. So we're really grateful to be joined by Dr. Eugenie Rudaya. She is a scientific associate at Rotman Research Institute at Baycrest Academy for Research and Education, where she co-leads the Visage Laboratory. She earned her PhD from McMaster University in psychology. Her research aims to better understand how vision changes in healthy and in abnormal aging, find new ways to monitor brain health with age, and to identify how we can improve mental and perceptual abilities in older adults. So she will be introducing these important topics to us and then reviewing one of her related studies. So welcome, and we look forward to hearing your presentation.
Thank you very much. It's really a great pleasure to be here. I hope you can all hear me well. Yes. Okay, perfect. It's really a pleasure to speak to you all today about our research, this general topic, and looking forward to hearing your questions about it. So I will be talking about how measuring our visual abilities and electrical signals in the brain can potentially help us detect Alzheimer's disease early on. So this is a brief outline of my talk. First, I'll introduce you to the topic of vision and visual perception and aging and what we know about that so far, brief overview. And we'll talk about what we know about how visual abilities change in the context of Alzheimer's disease. Then I'll introduce our study where we measured electrical brain signals during visual tasks as a way to, oh, we can't see your slides. Thank you so much. I forgot to screen share. That is quite important. Okay. So the first slide was just a title slide, so I'll bring it back for you. So as was introduced before, I'm a scientific associate at the Visage Lab that is also led by Dr. Alison Sekuler at Baycrest, Rotman Research Institute. Okay, I'll get to my outline slide. So we'll talk about how measuring brain, one of our studies looking at how measuring brain signals during visual tasks may potentially help in early detection for Alzheimer's disease. And then I'll discuss specifically our current study that's called Bright Spark. Okay. So of course, when we think about vision, the first thing that we might think about is visual health. So we know that as we age, our risk of developing a visual health condition such as macular degeneration, glaucoma, cataracts increases a lot. And there are many older adults. There's approximately 1 million Canadians that have some form of age-related macular degeneration. So that causes a loss of vision in the central part of the visual field. Other older adults may have glaucoma, which causes a shrinkage of your visual field in the periphery. Cataracts are also very common, and thankfully these are treated easily with surgery. And there's also diabetic retinopathy is also affects a lot of older Canadians. And this is important to keep in mind because This year, the Lancet report on the modifiable risk factors for dementia have added visual loss as a new risk factor in older age that, if addressed, may reduce the potential proportion of older adults developing dementia by 2%. So visual loss in older age is not something to ignore or set aside, but it is quite important to be able to see your eye doctors regularly and do everything we can to maintain their vision as best as it can be. So when we think about vision and aging, the first, besides health conditions that happen to the eye, just with if your eyes are completely healthy, there are natural changes that occur with aging, and one of those is presbyopia. So that's when you start requiring reading glasses around age 50 or so. And this really happens because of the changes in your eye. So that refers to the lens in the eye needs to shrink or contract, and it becomes less flexible as we get older. And that makes it more difficult to see print close nearby. And also the muscles in our eye also get more tired with age. So this is addressed fairly simply with reading glasses. However, aging also causes many changes to our brain. So our brain does age as well, and the neural function of the brain is continuously changing. And our visual perception is much more complex than simply reading text or looking nearby. And vision scientists, so I consider myself a vision scientist because in my research background, I really studied how visual perception works in the brain. And many vision scientists have devised various tools and procedures to study how our perception works for all sorts of visual abilities. So, for example, our ability to see if a line is oriented vertically or horizontally can be studied by creating multiple different stimuli that look like this, gratings of different thicknesses, different contrasts, different orientations. Our ability to recognize faces can be studied by coming up with tasks that show you similarly looking two people and asking you to recognize which one you just saw previously. Our ability to see motion, where if you're heading down the street and the road is making a slight turn, your visual system is processing the motion, the optic flow that is passing by you. And so vision scientists come up with these multiple random dot paradigms where you have many different dots that move in different directions. And we ask participants to report which direction do you see the dots moving? Is it left or right? And with various techniques, we can figure out how sensitive, how capable are you in seeing the specific type of motion. Another interesting, cool stimulus that has been studied a lot is our ability to see how people walk. So you might remember, you can probably recognize your neighbor just looking at from the back when they're walking down the street. How is it that our brain is able to distinguish, if it's a man or a woman walking, or is it your neighbor or somebody else? So we have created these types of stimuli, and we can manipulate the locations of the dots, how they move, etc., to be able to study how the brain processes various types of visual abilities. So with this type of research, scientists have been able to map out what brain areas are involved in processing various types of visual information. So just a brief overview of what we know so far is that once your light visual information hits your eye, it hits first the retina in the back of your eye, which is actually a part of the brain. And the retina has neurons that start generating electrical signals. And that electrical signal goes first in the middle in this lateral geniculate nucleus. And then once it gets to the cortex, to the brain, It goes all the way to the back of the brain to something we call the occipital lobe, or where the primary visual cortex is located. And once the information gets there, a certain type of processing happens. So specifically, the neurons are interested in just seeing if something is falling into the location in the visual field where it's looking, and what orientation, and whether it matches the orientation that it prefers. So you have many different neurons in here that are processing information at a very basic level. And then as you proceed down this ventral path, we call it a ventral path, but it's in the temporal lobe along the side of your brain. In this ventral path, subsequent, more complex information is being extracted by neurons that connect to this primary visual area. And as we go upstream, you have different areas that specialize in perceiving what shape something is, recognizing faces. What type of, is this a male or a female face? Is it my mother or is it my sister? And other things like the texture of objects and things like that. So this ventral pathway asks about what is it that I'm looking at? And a different pathway going up the parietal lobe, we call this parietal lobe, in the dorsal visual stream, is asking the question, where is it? So if you're processing motion and you're going in a certain direction, it's going to be processed more in the dorsal stream, or the relative orientation of things where you're heading is processed here. Of course, this is more complex than this, but the basic idea is that you can see that there are many different areas across the brain that process different type of information about what we are seeing. Now, when you go to the clinic, usually, the way that you typically know that your vision is being tested is you measure your visual acuity. So how small can you read the letter, which is important for reading, important for, being able to thread a needle. And also you might have seen this other test that looks at your contrast sensitivity. So how faint does the letter have to be for you to not be able to see it anymore? So how well can you see shapes when the contrast is very low? And when you measure these abilities in healthy older adults who have no visual health conditions, you see some declines compared to younger adults. So visual acuity on average goes down, and contrast sensitivity as well. But and that means that it will become more difficult to process information when you're going on a foggy day, and it's really hard to see. If you're driving in fog, you might have noticed that it's more difficult because of the reduced contrast sensitivity. But our world is much more complex than the two eye charts that I showed you, and there are many more tasks, complicated tasks that our brain has to do on a regular basis to process our visual information. So you might need to be able to see, where is your favorite food? So to distinguish your olive from a different vegetable that you might not like, the kiwi from a potato, and to judge the ripeness of a fruit, for example. You might need to recognize who you're talking to, whether it's somebody that you've seen before or not. And another common thing is, older adults sometimes report having difficulty navigating moving stairs, and that might be due to more difficulty with processing motion information. So overall, this is a really poignant quote by a 70-year-old scientist who has sort of introspected about how they perceive their vision changing with aging. And they were saying that just plain seeing in simplified situations, like in routine vision testing, seems as good and as quick as ever. But perceiving the meaning of a complex and changing scene is definitely more difficult and slower. I see parts as well as I ever did, but organizing of perception as a whole seems to be more time consuming and require more attention. So You may or may not have noticed this if you're an older adult. In my PhD research, I was interested to see whether this ability to group information across space is affected in healthy aging, in the context of specifically how we perceive shapes. So I'll walk you through a little bit of the process of how this research is done, and to tell you a bit more of how we understand sort of our ability to see shapes. So you might think, looking at this image, you see immediately that it's a snake, and you'll be able to, go and grab it if you needed to, or you can see sort of where the snake begins and how it continues. But our visual system has several steps for it to be able to identify this object. And this happens not just with any object. So like I mentioned before, in the primary visual cortex, in this first location where information gets into your brain, any neuron is only interested in one specific location in the visual field, and is only tuned, we call it tuned, is only interested to whether there's something in that location that corresponds to the orientation that it prefers. So for example, if you look at this, can you see my mouse? Let's see.
Yes, I
Yes,
can see
we
your
can
mouse
see it.
moving.
You can see my mouse? Okay, thank you. So if you look at this location, for example, this neuron prefers an orientation that's tilted a little bit to the right. But underneath that, the snake is tilting a little bit to the left. So this neuron wouldn't be responding really highly. But this other neuron over here is pretty much aligned with the contour that's underneath. So this one would be firing a lot. And so you have a gazillion neurons that are going to be firing a lot. And it is up to our brain to actually figure out which of these neurons that are firing actually are indicating an object that belongs together, right? So this one, and this one need to be grouped together to say that, oh, this is the curve of my snake. But these two are not related, right? So this is sort of the basic idea that what one higher level stage of the neurons need to be able to group together information. And they need to be able to ignore the noisy information that is not related to, the patches that are from the background, for example, shouldn't be grouped together. Okay. So I studied this question in older adults. And so we recruited healthy younger adults, undergraduate students, and healthy older adults. And we brought them into the lab, and we presented multiple trials of these images. And they would look at one image and it would flash really briefly on the screen. And they would have to say whether the gap in the sea was in the bottom right, bottom left, upper right, or upper left. And then here you might be able to see it fairly easily. Here it's a little bit harder to see. And then in this case, it's much harder to see. So these are three different conditions that we looked at. And regardless of the conditions, what we saw is that for older adults that are in dark, they needed the stimulus, the image needed to be on the screen for much longer for older adults to be able to see this information to accurately report the gap than younger adults. And now this might be because we're having more trouble grouping together the elements together, or because we're having trouble ignoring the noisy elements that are unrelated. So to look at this question, we actually manipulated the stimuli in a different way, where you had on the left-hand side, you can see that I have a spiral that the participants were looking to detect, where the orientation of the spiral. And on the left-hand side, the spacing between the background and the contour is exactly the same. But on the right-hand side, the spacing of the background is much more dense compared to the contour elements. And what we saw is that for older adults, adding more clutter into the background impacted their performance a lot more than for younger adults. So there's a difficulty in actually ignoring this noisy information. And furthermore, we looked at how the brain responds to this perception by using what's called EEG, electroencephalography. So this is a photo of one type of EEG device that we use in the lab, and there are many different kinds. And in this case, it's really, these are, I don't know if some of you hopefully have already seen them, but in case not, so you can see that it's a net that you put over your head, and all it does is passively records. It touches your scalp and senses your brain activity underneath the scalp, and basically records all the brain waves that are going on while you're doing specific tasks. And the way we do this research is that we present the images on multiple locations. And at the time that the image is presented, we call that 0. So at time 0 over here, what you're looking at here is the average. If we look at the blue line, which are the younger adults, this is the average change in brain activity in the back of the head, in the occipital area. Change in brain activity at the moment, at 0, is the moment when the stimulus happens. So when the stimulus appears and they're trying to detect this spiral contour, we see that there's a little blip going up and then a blip going down in younger adults. So there's brain activity going up and down in the potential, in the microvolts here, in younger adults. And in older adults, you see that this activity is much increased. So it's as if older adults are having more difficulty doing the task and are also engaging their brain more so in this during this task. So you see a much larger amplitude. And in research, we like to see large amplitudes because if the amplitude is very small, then it's very hard to see differences in the effects. So there are other, of course, researchers that have studied how aging affects different types of visual abilities. And I'll just give you a brief overview of what we know so far. So perception, researchers have studied how aging affects different types of motion perception. And what they found is that our ability to see how motion horizontally, so if you have a portion of these dots, your task would be to say whether the portion of these dots is moving to the right or to the left. And all the white dots would be moving randomly in a noisy pattern. And compared to younger adults, older adults need a stronger signal to be able to detect this horizontal motion. But there is no difference in how much signal older adults need compared to younger adults to detect this type of radial flow. So when the dots are moving towards you or away from you in this radial pattern. Their ability to see biological motion, like I showed you before. So in this study, the researchers added extra dots that moved all around, and that makes it more difficult to see the walker. And here, older adults also had more difficulties to see which direction the person is walking. Now, what's interesting is that, so using various control measures and by recruiting older adults who don't have any visual health conditions, we know that these changes that we see in various visual perceptual abilities are caused by changes in the brain. So our brains are aging, and that is causing our visual perception to change in different ways. And in this interesting study, they've looked at a large number of older adults, and they have tested them on more than 19 different visual tasks. And what they saw is that although most of those tasks show change with aging, those changes are different for different people. So it's not the case that if somebody's having more trouble visually, all the tasks that you're measuring decrease in the same direction or in the same rate. Some people have more difficulty with some tasks, but not others. So the aging effect on these various visual abilities is actually different and distinct across individuals and across tasks, which makes the research really interesting. So, but now what do we know about how vision changes in Alzheimer's disease? Well, we know that Alzheimer's pathology, so these are the protein that are associated with Alzheimer's disease, like amyloid and tau, they get deposited in the brain in various areas and also in the retina. So there are some other researchers that are using images of the retina to be able to detect Alzheimer's early. And that shows a lot of promise as well. And we know that the brain is, of course, affected in Alzheimer's disease. And what's complicated and interesting is that the areas that are affected by the disease varies across people and across the stages of the disease. So in this study, they showed that there's, what's called a typical Alzheimer's disease, where it starts, it eventually progresses to affect, temporal, parietal, frontal areas of the brain and also in the middle. And as you might remember with the visual streams that I showed you before, a lot of the areas of the visual stream are impacted in Alzheimer's disease. But there are other types of Alzheimer's disease that affect other areas, not everything that you see in the typical. There are different ways of advancing in the brain, and that is related to the symptoms that you might see in the individual. And even though Alzheimer's disease is something that we think about that affects cognition or memory mostly, it's actually, visual symptoms are actually quite common as one of the early symptoms that accompanies Alzheimer's disease. So people might have difficulty judging distances or perceiving the direction of motion, or judging the depth of a step. But I think that it's more difficult for people to introspect about their visual ability. This is my subjective sort of feeling, than noticing that they forgot where, the name of somebody that they know really well. With Alzheimer's disease, there's also greater difficulty seeing in low contrast. So we talked about contrast sensitivity before, but that is also something that is affected even more in Alzheimer's disease. So, which means that going downstairs that don't have a yellow sort of bar at the bottom of the stairs would actually be really difficult, because without the contrast, you won't be able to see where one step ends and the other step begins. So this study is one of the studies that inspired me to go to study, to shift my research focus from healthy aging to Alzheimer's dementia. And it really illustrates how how our perception of contrast and contrast sensitivity is an important part to keep in mind when caring for individuals who have Alzheimer's disease or other types of dementia as well. So for individuals with advanced Alzheimer's disease, one of the issues is that they sometimes don't eat a lot of food. especially in sort of long-term care. So in this study, Dr. Cronin Golom is a vision scientist, and they devised this study where they manipulated just the color of the plates that food was served in. So traditionally, this institution would serve food on white plates with white cutlery. These pictures are not from the original study. This is just for illustration purposes. But typical food that is served is kind of our bland white color. And so the contrast between the plate and the food is really low. And what they did is just change the contrast by using a bright red plate, or in another study, it was a bright blue plate. And they just looked at how much food and drink was consumed during lunches and dinners for 30 days. And they found that just changing this changing the plate increased food intake by 25%. And you can see on the left is baseline is eating with the white plate. Then with the red plate, they eat more, and back with the white plate, they start eating less. So you might not really think that contrast is, it's not something that we think about, or visual clutter is not necessarily something that we think about in terms of adapting the environment for older adults with Alzheimer's disease. But this was a clear example of how understanding how vision changes with Alzheimer's disease is important to know how we can actually adapt the environment and help individuals have a better quality of life. So another really interesting finding in terms of the effects of Alzheimer's disease and vision is this study here from back in 2006 that looked at how we see this optic flow. So I mentioned earlier that the ability to see radial flow. So this is when you're going down the street and the cars and the road is going past you this way. So this is optic flow. In this task, they ask people to say, is the optic flow more coming from the left or from the right? And then they varied the coherence of these dot motion. And what you can see is that younger adults compared to middle age, compared to older adults, the effect is very small, or there's no significant difference. But older adults with Alzheimer's disease, dementia, have a much harder time doing this task. So that is something that seems not to be affected in healthy aging, but is affected in Alzheimer's disease. Now, so this led, so in these studies that I've showed you so far, people have tested individuals who had a diagnosis of dementia already. But currently, it is a really important goal is actually trying to detect Alzheimer's disease early on. So there's a really high need to develop better tools to actually detect Alzheimer's dementia much early on. And this is because, we know that these proteins that affect the brain start accumulating in the brain sometimes many years before any symptoms appear. And the symptoms or many years before, somebody gets diagnosed. Some of the earliest symptoms is this cognitive decline that is currently being measured in the clinic. And if somebody has significant cognitive decline more than typical individuals of their age, they might get diagnosed with something called mild cognitive impairment. And if that mild cognitive impairment is due to underlying dementia diagnosis, this offers a window of opportunity to actually intervene and give, enroll the patient to a clinical trial that is testing a new drug, or there are already drugs on the market currently today that are helping to prevent cognitive decline, but they need to be given earlier in the time course of the disease. And so currently there's a big need to find better ways to identify individuals who are on this Alzheimer's disease continuum, but before the individual themselves notices any cognitive symptoms, because that takes time. And then from noticing to actually getting diagnosed, that takes also some time. And so if we can develop ways to actually facilitate this detection or screening, that may help get treatment sooner. So in our lab, we are asking the question, can vision-based tests help us detect somebody who is on the Alzheimer's disease continuum, but earlier on than is currently done with things like cognitive testing? So in this study in our lab back before the pandemic, we devised a simple task with looking at face perception, looking at this contour integration that I showed you before, and also at motion. And then we measured brain activity using a very simple device that has only 4 sensors. And we asked participants to tell us which face was shown previously. And we looked at the brain responses. And we see that with older adults who have mild cognitive impairment, they show a delayed response in their brain activity to this task. Now, in the contour task, we asked participants to say if the contour is facing left or right. And then we looked at how difficult it is for them to see the contour. And what we see is that participants who have mild cognitive impairment are less tolerant to clutter. So they actually have greater difficulty seeing this contour in the clutter. And this clutter density measure that we obtain is correlated with their global cognitive function. And moreover, we also see a delay in the brain response recorded with this simple brain sensing device when they're doing this task. So that led us to, this really is showing us that performance and the brain electrical responses during simple vision-based tasks differs between older adults who have normal cognition and those who have mild cognitive impairment. And using this task, we might be able to assess brain health outside of a full neuropsychological test, but that may be helpful to screen to see if somebody may have mild cognitive impairment. But really the key question for this to be very useful would be, can vision-based tasks predict cognitive change or the development of dementia? Because some people with mild cognitive impairment will show decline in the near future, but others may show it much, much later, and others may not at all show decline. So what we don't know yet is whether performance in these visual tasks that we have developed can help us predict whether somebody will develop Alzheimer's disease or not. And that is really the goal of the Bright Spark study that we are currently recruiting. Bright Spark, measuring brain activity to predict cognitive health in mild cognitive impairment and Alzheimer's disease. So this project was funded by the National Research Council, and it's done in collaboration with Bruyère Research Institute. And the investigators are listed here. And the goal, so who we're recruiting, Bright Spark study is being conducted in Toronto at Baycrest and also at Bruyère Research Institute. And we are recruiting older adults who are between 60 and 85 years old, who either have a diagnosis of mild cognitive impairment or also a diagnosis of Alzheimer's dementia as well. And we are recruiting controls and those who have subjective cognitive decline in a parallel study that is very similar to this one. Now because these are vision-based tasks, we need to make sure that participants don't have any visual health conditions that I mentioned about, because that will impact, their performance in our tests. That is something very important to look at in the future, how performance in our tests will be affected by these very common visual health conditions. But as a first step, we need to have a group that is free of these visual health concerns. As well as, participants need to be otherwise in good health, so no severe or moderate anxiety or depression or a history of stroke, etc. And participants are asked to take part with a study partner who knows them well for the last 5 years, who can provide information about how they function in everyday life. And in the study, participants will be screened, and then they will come at baseline, they will come for 2 visits, 1 to 2 weeks apart. And then the participants will be asked to come back 6 months, 1 year, and 1.5 years later. And I'll give you a very brief overview of what the study looks like, what you will be doing. So we will be testing your visual acuity and your contrast sensitivity. And we would also do a full neuropsychological testing battery, just like you would do in a clinic, to really characterize well our participants in terms of their cognitive function. We will also collect information about your demographics, past medical history, subjective cognitive function, how acceptable the study is, how did the study go for you, and we will interview the study partner to find out the functional abilities of the individual. And then, of course, we're going to have our EEG testing session. So this shows you a little bit, this is a cap that a participant will wear on their head. And then we add 16 electrodes on your skull, and a couple of electrodes just above and below your eye. And then you will be sitting in front of a computer screen and doing a few simple tasks that are based on vision. In the second visit, we would only do the visual acuity and the EEG testing session. So very briefly, your EEG testing session would consist of doing this contour task that I talked about, a bit of a break, another task where you have to just press a button as soon as you see some stripes, more break, and then you would have to look at moving dots. For follow-up visits, we would repeat, again, your EEG. At 12 and 18 months, we would also repeat the neuropsychological testing. And what is it that we want to find out in this study? Well, your participation in baseline visits will help us answer, are tests acceptable? Is it simple to understand? Is it, are you feeling comfortable doing this test? Are the brain activity measures that we are interested in reliable from day to day? Because we don't want to have something that, gives a negative result one day and 1 week later it will give a positive result. So we want to have something reliable. And we will see how easy is it to distinguish between those who have mild cognitive impairment, mild dementia, and controls with these tasks. And then the question that we're asking with follow-up visits is, does the brain activity during our tasks that we measure at baseline, can it predict the cognitive change that you will see in some people and not others at 18 months? And the ultimate goal of this study is to validate a new test that could be used in the clinic to help screen or diagnose mild cognitive impairment, but crucially also to predict whether somebody will see cognitive change or not in the near future. And so if you're interested in this study, we really encourage you to contact us either in Toronto. This is the contact information for our lab, where Zohar Rabi is our research assistant, who will be glad to assist you. And if you know people in Ottawa, or if you're connecting from Ottawa, you can contact the Clinical Trials Unit at the Bria Research Institute at this number. And thank you all for your attention. And I'm open for any questions.